So now in this video, we combined some topics that we covered in earlier videos. I was using one of the NOR gates on this integrated circuit, so those pin numbers don't align to what we have here. So there is an input, 1 and 2, and then number 3 is the output. Whereas the NOR gate down here, we have an input at 6, input at 5, and the output is 4. So the two outputs are together and then they're flanked by inputs. Same with over here, except for they're shuffled down one spot because the positive supply is up there, negative supply is down there. But in any case, what this is a NOR gate. So don't worry about the output right now. It's actually inverted. So ultimately, this circuit becomes an OR gate. The NOR logic gates, though, from this integrated circuit really can't provide any current. It barely lit the LEDs. I had higher value resistors, but if I used lower value resistors, the voltage output would have been even worse. We looked at that in a recent video where I measured the voltage output. It fell really short of what it should be, even though we didn't demand much current. But in any case, let's get back to this. So a NOR gate means that we need both inputs low for the output to be high. So you notice blue LED lit up. The output of the transistors is actually low, but they invert the signal they get. So for the output to be low, we have to get a high input to the transistors. They're both getting the same voltage. So output is actually high for the NOR gate, low over there because it's inverted. If we have enough light on the trim pad, you can see it's or the light dependent resistor, it's to the positive supply, fixed resistor to the negative supply. So enough light makes it so that the light dependent resistor does not conduct, when it's dark, does not conduct very well, and so the voltage gets sucked down, just like a trim pot there. If I put the trim pot to the positive supply, now it doesn't matter if I cover the LED or not. So in any case, now we have an OR gate. If this one's high, or this one's high, then the output will be high now that we inverted it. If they're both low, as you see there, now we have a low output. So that would be a normal OR gate, which the full circuitry makes. But this is a NOR gate. Hopefully that makes sense. We covered those in earlier videos. I'm not going to dwell on them too much longer. So the reason why we are doing this, I have 220 ohm resistors protecting both the blue and the red LED. You can see how bright the blue LED is right there versus the red LED. It's even more annoying in person. It's quite a bit easier to tell it's brighter. But in any case, we couldn't really light them up very much from the output. As we saw, we lost a lot of voltage in a recent video where I measured the voltage. So we got the output coming to the gate of both of these. So we got a P channel enhancement mode MOSFET up there, N channel enhancement mode MOSFET right there. They just respond to the voltage at the gate. And so when we have a high output at the, remember, it's going to get inverted when it comes to an OR gate. But when we do have 5 volts coming out there, that turns the N channel enhancement mode MOSFET on, whereas it turns off the P channel enhancement mode MOSFET. That's because the gate is the opposite of the channel. It's kind of like a capacitor right there. So you make the gate more positive, the channel becomes more negative. It's N channel enhancement. So we have a current path there. This is P channel enhancement. It needs to be more positive. So when we get the output negative enough, that makes the gate negative, makes the P channel there more positive. It conducts. That's the simplest way to explain it. This is N channel enhancement. So when the channel gets more positive, remember, negative, positive, it turns off right there. It's N channel enhancement. Hopefully it makes sense. And then we got the lower value resistors right there. So this is all basically stuff I covered before that I mentioned now. It's a review, but it's kind of confusing stuff. So yeah, we got low, and then now it's dark enough, that's low, or I could turn the lamp. I also have an override switch right there that I put on there. So I'm just reusing circuit I used before. So that's kind of a review. But I recommend you see that video if none of this makes sense. So now we got the multimeter there. I'm going to set it to measure voltage. Black probe, I clipped this alligator clip too. Other end, we got a jumper there to the negative supply. So that's basically our reference voltage. The voltage in relationship to 0 volts ground is the red alligator clip. And I'll zoom in so you can see where I'm attaching this. So the two LEDs, the cathode of the blue LED, the anode of the red LED, connect to that jumper there. You should be able to see that pretty good. So I'm going to measure the voltage where they connect right there. And there you can see it's practically the full positive voltage. So we are going to lose a little bit. Transistors do take away a little bit of voltage, generally speaking, no matter how well they conduct. But if you saw the last video, we were limiting current a whole lot more through the red LED, and I think we lost like a whole volt. It was like down to 4 volts when the red LED was lit up, and now we got like 4.88. So we're losing, it looks like maybe 100th approximately of a volt instead of losing 1/10 of a volt for the most part. So now to get the output low, we need to go low on both of these. That's right. There we go. And there you can see that's connecting to a ground pretty good right there, 0.041. Again, not as good as the integrated circuit with no load, but with the load, we're doing pretty good right there. Again, the power supply voltage, negative supply, is 0. So when the blue LED is lit, we are practically at 0 volts when I get the light dependent resistor dark enough right there. So again, earlier video I measured while we were lighting the LEDs directly from the output. Current was a whole lot lower. We were using 4 times the resistance, 1000 ohm resistors, and therefore we were getting about 1/4 of the current if we were getting the full voltage across them. We weren't even getting the full voltage across them, so it was going down even more than that. You know, again, topics from a whole bunch of other videos. We're not going to dwell on that way too much. Again, I showed the schematic. We can take a closer look at the physical circuit now. I'll get the multimeter out of the way there, and there we go. So we need to tie the gates together to get the same gate voltage, and then the drains are tied together because that's the output for the transistors. The input is the supply voltages there. This is our control gate. So we'll zoom in, and hopefully you saw the pin layouts there. So the drain was the supply voltage, basically the input. The gate's that little blue jumper there. The signal we're getting is from the output of the integrated circuit. I could have measured those voltages, but I did that in a recent video. So don't want to waste way too much time taking the same voltage measurements over and over again. So yeah, gates tied together. They're getting that signal voltage right there. And then the source of both of these are tied together. So that's P channel enhancement, that's N channel enhancement. They work the same way, except for their chemistries are the opposite. So one turns on with a high signal, the NPN actually does, and the other one turns on with a low signal, and then they turn off alternatively. And then the power that they provide at their output is opposite of each other, you know, so you give their inputs the opposite as well. So hopefully that makes sense. And then we got the LEDs, I explained those before. Again, usually I use a 1K resistor for the blue LED because it gets brighter. I normally would anyways, but this is a demonstration circuit I want to show. Even with the higher amount of current going through the blue LED, the transistors are helping to get almost the full supply voltage. Way, way, way better than what the integrated circuit does. So you can use these integrated circuits to control transistors. They're really good at that if you need to power something. They just are good at giving a signal. And as we saw, with no load, which these transistors are no load, they just look at the voltage. Just a slight current changes. You see when this is changing, a slight current shifts as they change from one on to one off in this case. But that's it. After that, the voltage is just steady when it comes to the signal. So we're going to get the full rail voltage as we saw, which that does when you're not providing a load. So yeah, I think I covered pretty much everything there. So hope you enjoyed. Make sure you check out one of the other videos I'm posting on the screen, and check out the links down below. They all help a lot. I'll see you in the next video.